Hello everyone, welcome back to ECE350, lecture 15. Today we're going to talk about generator EMF. You all know what the difference between generator and motor. We're going to ask you the same question in the class. Okay, for a generator, you know that you have to apply some kind of mechanical force to rotate the rotor. Rotor has current carrying conductor that's produce magnetic field. So for here, we are using only one conductor over here, that we're rotating this conductor using a mechanical force. And also at here, we're connecting a load, which is my bulb here, using two brush, right? So, and this coil is rotating in the middle of magnetic field B, right? So magnetic field B is in the Z direction, and rotation direction for now is the direction of the rotation for this particular arrangement is n hat over here. What is n hat? We're going to talk about that, what is n hat is. Before we understand that, we're looking for a linear velocity, all right? So r omega, and the r is half of the width. There's a width over here is w, so r is w over 2. Then your u, the linear velocity, u is n hat omega w over 2. And n hat is the normal to the surface of the loop. So n hat is a normal to the surface of the loop here, okay? So then if you now cross n hat with z hat is the direction of B, you get x hat sine alpha. So this is the cross product between your velocity of the loop and the magnetic field. So that is very important over here. You know that it's very important because we discussed them in the last lecture with the motional EMF. All right. So for us, we have four sections. We have 1, 2, 2, 3, 3, 4, and 4, 1. But this two section does not contribute to the voltage, because for these two sections, this product is 0. Okay, so only 1, 2, and 3, 4 contributes to the induced voltage or motional EMF. So for 1 to 4, if you come 1 to 4, I would to go 1 to 2 first, and this one is 0. Then I have to 3, 4. Then this one is 0. So I have two sections over here, 2, 1, and 4, 3. So for that, if we put it back here, the limit is half L over 2 to L over 2. And then over here, same thing, L over 2 to half L over 2. There's the length. Total length is L. So half this way, half that way. Then this is your U. This is your Z. Again, this is U. This is your Z. Why this one is negative over here? If top one is positive, this way, U, right? And this one would be going this way here, that would be negative. So that's why it's negative over here, okay? These are the linear velocity from your rotational velocity. So let's go back here. So rotational velocity omega, linear velocity is the tangent at any point of the circle. That's why if you rotate this loop, you're going to make a circle. So at that circle, you get u on this way, and it will be negative u on the other way. So that's why negative sign over here. If you finish this in dot product and integration, you'll get this value over here, right? Over here, W and L will give you the area of the loop, right? And omega is the radian per second, rotational velocity, and B0 is the magnetic field density magnitude, and sine alpha is the reference angle, all right? Alpha could be your omega t plus 0. So if you're not starting at 0 when time is 0, then you can have a reference angle C0 right here. So that this one could be written as A omega B0 sine omega t plus C0. That's your motional EMF for a generator. Again, that depends on your area and omega and also B0. Right, and you can get the same thing if we use the Faraday's law. So flux, if you have flux density, and if you know the area, if you integrate that over the area, you get total flux. So that would be right here. Then if you now take the the derivative of that flux with respect to time, you get the voltage. And they both have the same expression, so you can go either way. So we're going to talk about this in the class. And also we're going to talk about this in the class. If you have a both, now motional and transformer, you basically add them together. This is the motional part here, this is the transformer part here. You add them together to find the total EMF. All right? We're going to do this problem in the class. And we're going to talk about this tech brief in the class too. That's all. We're going to get to the lecture 16, who's going to talk about displacement current.